Good day. Welcome back to join me in to learn about embedded system design on ARM Cortex M4 series. Today is day 19. I hope you have been revising the previous sessions and you're getting familiarize yourself with the different registers and how the peripheral is used and how the bus connections are happening and what is all the registers that's all involved for the past. If not, please go back and revise it so that you can familiarize yourself so that it would be helpful and easy to follow through from the next coming sessions. Today is day 19. Today we're going to learn about the implementation of task scheduler as part 2. The last session you learned about part 1. Today is part 2. Before getting in, I will do a recap of what we learned from previous session. This is what you will be learning today. You will be learning today to implement the scheduled algorithm. That's where we stopped in the previous session, but that's what you're going to learn today. Before jumping in, I would like to introduce myself, whom I'm representing. I'm representing A2DG. It is a startup by Anbukarasu brothers, my brother Alex and myself Arul in 2023. If you want your website to be built with all the user interface, then please do contact Alex. He's very good in web designing, and he will do everything from start to completion. So please do contact him. We both gathered over 20 plus years of experience in the industry, and we would like to put it out there so that it will all help you to mold yourself to be a better professional. To do that, our mission is to convey our knowledge and our experience to at least about 100,000 future professionals through our online courses. The main advantage is you can study at your own pace wherever you are at any time, and that is very good about it. Little bit about me. I am Arul Prakash Anbukarasu. You can call me as Arul or API, as persistent as I would like to be, to share my knowledge and experience to you all out there, so you would be able to be molded into a better professional. I have 20 plus years working in various industries in different countries in Australia, Italy, Singapore, and India on these major industries: renewable energy sector, that is in solar and wind, power systems, that's lead acid batteries, network embedded systems that's connected to ATMs, TCRs, and POS, banking automation systems, and smart parking operations. My expertise lies on these three: embedded systems, VLSI, and project management. A short announcement to make. I categorized into two different categories. First is the YouTube viewers. In order to get a free e-certificate, you have to at least watch 28 videos. At the end of every video session, there is a separate link. You have to click on that and you have to fill in all the details and then send it across to us. That will count for your attendance for that. Due to YouTube regulations, all the videos that I am going to upload into A2DG channel won't live there forever. So after 2 or 3 days, it has to be removed. So in case if you have missed anything and if you want to go back to revise, unfortunately you can't. So that's why I strongly recommend you and advise you to join in one of our internship program. This will acquire you to get a internship certificate, and that is worth a lot when you compare with the others who have no training at all, no knowledge about it, and use it right at the top. When you land into that first job working with senior engineers, they will take this 30 days, and the project managers as well, that they will value these 30 days, and that's a lot in the industry because they don't have to teach you the basics, so you are there and you will start up and start running. Not only that, you will have a separate login to log into our LMS learning management system portal, and you can go through each and every day session. So once you watch through one day and click complete, that counts to your attendance. At the end of 30 days, when you click finish, then that does the auto generation to produce you the certificate. Not only that, you would be able to access to all the course contents unlimited times. So that means you can get all the PDF materials from the source for the materials, all from the courses, and all the source codes and all other reference manuals, data sheets, etc. You will get it. And also, unlimited access to course videos. That means you can pause, you can go to do other activities and come back and rewatch it again. Or if you want to recap, if you want to go back few sessions back, you can go back and watch it, because it's all for you to keep and you can do whatever you want with it. And in case if you get stuck in the learning curve, please contact our backend team, and they will be able to support you to make you move along in your learning curve. These are all the materials and components required. If you haven't bought already, please do contact Pantex Solutions. They are big in manufacturing company, and they would be able to assist you to acquire you all of this. The more you have your hands on with training, the more knowledge you acquire. So please do contact Pantex Solutions. So shall we continue to get into the further tasks to see what ahead lies for us in these scheduling of algorithms? So let's get in and get started. Before jumping there, I would like to give you a recap of what we caught up from the previous session. As we learned, a scheduler is a program that manages the execution of tasks or processes. When we talk about tasks are nothing but it is also a function, but every task will have its own private stack. So that's the difference between the function and the task. And there are plenty of algorithms out there. This session is all about talking about round robin scheduling. So the scheduler will be responsible to determine which one to be run from the CPU time, and also it allocates the memory to the tasks. And there are plenty of algorithms out there. One has the priority scheduling and round robin scheduling. We'll be learning about round robin scheduling. What is a task? A task is a small program or a piece of code which is nothing but a function which is performed to do a specific job when it is allowed to run from the CPU. As we learned earlier, it has its own private stack that preempts the value, so that if you want to move to a different task, it saves the current task and then goes to and do the next task to do it. Unless otherwise you delete it, it will be there, so the task will be returned back to for the microcontroller to run from CPU. What is preempt? Preempt is nothing but it saves the context of the current task, and when other interrupt occurs, it saves that and moves to the task 2 or the next task. So they allow the opportunity to make it run, to make it possible to also attain to the next task. That's the allow control is called preemption. So that's what it is. The ways to implement scheduler, there are multiple. If there are multiple tasks in your program, then we're going to cover. This session is all about round robin, and also we will be learning about, you already learned about what context switch operation is. Context switch is moving from one task to the other switch by halting one and moving into the other one. So that is the context switching, that is switching in to save and switching out to retrieve data. So that is what context switching is. And we'll be doing that in the round robin fashion with the time slice. So every task will be scheduled to allocate a time frame. So it has to run on that particular allocated time, and we will be using sysdig handler to carry out that context switching. We learned elaborately about round robin scheduler. Round robin is a scheduled algorithm used in computer operating systems. So comparatively, every task will be aligned with a specific allocated time. So once if the task 1 overruns the time, that context will be saved because the time limit is finished. So it will move on to task 2, and it will run for that set of time, and then if it finishes, then it will move to task 3. For instance, if it doesn't finish, then this will join in the queue at the end of the queue. So that means it goes in a loop, links. So likewise, once it finishes task 3, it has to go back to task 1. So this is where the context saved in this private stack will be retrieved by context restored. and the task 1 will be operated. So likewise it goes in a loop, goes in the section, so it doesn't go back to the main function as we know that, but this is the scheduler, so it schedules accordingly 1 2 3 and then finishes, and then once the down counter reaches to 0 it goes back to task 1 and so forth, so it will do the next operation. This is the we learned from previous session. We're going to learn about scheduling 4 tasks. So every task is linked to its own private stack. So T1 is stack T1, T2 is stack T2, likewise T3 and T4. By default, the PSP thread mode will have all the tasks scheduled in it. For example, when a sysdig handler, when an exception occurs, it moves from thread mode to run into the handler mode from the scheduler, and the scheduler will only run in the MSP handler mode. MSP is nothing but main stack pointer, that is in the handler mode. Whereas in PSP, it is a normal operation that runs on thread mode. PSP is nothing but processor stack pointer. It has a choice of selecting between the thread mode or the handler mode. In the in the thread mode, it has a choice of selecting whether it has to be in the PSP or MSP, but you need to configure that in the code to make sure the tasks run in the PSP mode. So that's done in the configuration of the code. And briefly, we learned yesterday about how the stack assessment in Cortex M4 STM32F411, as you know, the stack pointer operates in full descending mode. So at the end of the SRAM, the stack starts to pile up. So at the end of SRAM, first stack, task 1, and all the tasks has to be allocated with equal amount of time, so that it works with the round robin. So we're going to learn about scheduling for 4 tasks, and 1 kilobyte is scheduled for each and every task. Now, talking about the policy, we will be using the round robin preemptive scheduling, which means this one doesn't have any priority. That means if task 1 doesn't finish in 1 millisecond, it will move to task 2, and if task 2 completes in 1 millisecond, it will go to task 3. If the task 1 can't finish in time within that 1 millisecond run, then it will go to the end of the queue and will start again. By doing that, this will save all the context in its private stack. So when it comes back, it will retrieve the data and start to run. So that's how the policy selection is scheduled. So we recap that. And the context switching is from switching in and switching out, that is saving the context and retrieving the data. So that is what context switching is. And explaining that within an example, ARM Cortex M4, generally everything inside will have a state. State is nothing but it is registers, form of registers. So the processor core will have the general purpose registers, ALU, the status registers, and the special registers, along with all these additional interfaces to link to the processor core. And these are all the core registers. This all has to be saved into the stack frame. By default, it will save the stack frame 1, which you'll see in the next slide. And the first R2 to R7, it's R2 to R0 to R12 is general purpose registers. R0 to R7 considered as low registers. R8 to R11 considered as high registers. And the stack pointer is R13. As you know, the stack pointer consists of 2 modes, the processor stack pointer and the main stack pointer. The processor stack pointer is where the normal operation happens. It will be in the thread mode. And the main stack pointer is where the handler run starts, so that will be in the exception handler mode. There is a link register and the program counter and the program status word. So you need to move the stack pointer to program status word so that the scheduling will start to take place. So all these registers all called special registers. The PSR, fault mask, the control register, the exception mask registers, these are all called as special registers. And this is how the context saving and retrieving happens, as we learned from previous session. First, running T1, if the time period finishes and it has to go to T2, it will save the context of the T1 in its private stack and save that PSP value of T1, and will get the current PSP value of T2, and it will start to retrieve the data from T2 private stack, and it will start to run T2. Doing saving the context is by push instructions, and that is coined as context saving. By using pop instructions, you're retrieving the context from that private stack, and that's called context retrieving, and you got to use pop instructions for that. In general, in stacking and unstacking in any function, first you have a task one running, and if suddenly there is an exception happening, that means stacking by push instructions, it starts to push, and it loads all the value in the stack pointer in this format in full descending. So by default, it will have all of these registers, R0, R1, R2, R3, R12, LR, all this. And it goes from stacking to exception handler. So it moves from thread mode to handler mode in the MSP, and it will go back to T1. After that, it will do the unstacking. Unstacking is popping out the retrieved data in there. And this happens in a normal function. But in scheduling, this is how it happens. So the task one happens, and then there is an exception. It starts to do push instructions by stacking. It goes to the exception handler. Instead of going to task one, all these registers will be loaded and stacked by default on the stack frame. Instead of going to task one, it will go to task two. So this is called scheduling. So the process inside, it's almost as identical as a normal function, but scheduling with round robin, this is the difference. In general, the stack frame, by default, these are all the registers it will be saved initially: R0, R1, R2, R3, R12, LR, program counter, and program status word register. These are all saved as stack frame 1. So if you need to save the rest of the other registers, say R4 to R11, and the PSP, the stack pointer, and the other registers, if you want to do that, you need to write a code for that, and you got to save that by manually writing that code. And also you need to generate some assembly language code, so you got to change from stack pointer to program status word so that it can start to schedule. So you will be learning that today. We learned about configuring the sysdig timer. So to run the system clock with 16 megahertz to generate 1 millisecond, that is 0.001 second. If you want to generate the delay, this is the formula: delay equal to n divided by sysclock. We know sysclock, and we know what the delay we want, 0.01. System clock is 16 megahertz. If you put that in this formula, and you get n is equal to 16,000. So this is the reload value that you got to load in the reload value register under sysdig handler, so that it can generate 1 milliseconds for each and every task time frame. So for 1 millisecond, it's 16,000 counts. So for 1 microsecond delay, you need 16 count. For 1 count, it is 0.0625 microsecond delay for the sysdig handler to run. And this is how the saving context of T1, the task 1, from stacking frames. So as soon as there is an exception happens, the stacking starts to happen, and it goes to the exception handler, and via the stack frame will be saved in by default it will be saved in here, and then once it runs through the exception handler, the other stack frame 2 is saved here manually by pushing instructions. So once it's finished, then you need to retrieve the data, because you ask it to move to task 2. So task 1 context will be saved. So retrieve, you have to go the other way. First you need to retrieve SF2 and then SF1 on the task 2 area. So that's how the retrieving unstacking happens. And initially all the stack will be loaded with dummy, so you need to write that in the form of code, and you need to set all of this. And to initialize the stack, you got to start with the dummy data. And dummy data also, you got to save all these registers in the stack frame. The XPR will have its program status word. You need to change from stack pointer to program status word, and that will allow you to do the scheduling. When we talk about the program status register, you need to consider about this T bit, because ARM uses thumb instruction mode, thumb mode, so you need to set this T register. And also you need to use MRS register to read special function, and use MSR instruction register to write to that special function registers. And the program status word value will be 0 cross 0 1 1 2 followed by 6 zeros. This one is for thumb mode, so that's why it's there. And the return address of PC, it will be asking the program counter once it finishes the task 1, and it asks to go to task 2. And the link register will have the exception return value, which controls the exception exit. And this is the exception exit because we are running in the thread mode using PSP with non-floating. The others will run in the MSP with floating. So you got to load this value into the register for the execution return behavior into the task handler. So that's all we learned from previous session, and from here part 2 continues. So we went and we created all these macros from the previous session. First you declared the size stack, and you scheduled the size stack, and then you created 4 tasks, and then you have given the SRAM start, the SRAM size, and the SRAM end. And then you went and declared all 4 different states, and its start and the end. And then you schedule the stack start. Further along, you also created and learned the function. You need to define the system clock for 16 megahertz, and then you're going to define that system clock is going to be your sysdig time handler will be your system clock. And then you need to initialize a sysdig timer, and you're going to link this timer with the tick hertz. And then you created 4 different tasks, and also you enable the processor faults to include all the process faults, all the hard fault, usage fault, bus fault, and manage fault, to in case if your interrupt runs on some error, you want to find out what error that is fault. To do that, you need to enable the SHCSR, and you need to set these 3 bits as usage fault, 18, 17 bit as bus fault, 16 bit as mem fault. You went elaborately and you learnt all of this in the fault handling session. If you have any doubts, please go back and refer there, and you will be able to understand. And also we went and copied all the hard fault handler and the mem manage fault handler, bus fault handler, to include in the program. So when you face any handler error, you can see which error it is. If it is a mem manage or bus fault or usage fault, whatever, this will show to us in the console window. And then you started off learning with the sysdig timer initialization. First you got to load the current value, and then the reload value register, and the count value is by including this formula sysdig tick hertz -1. And then you have to clear the register first to reload the value, and then you reload the value with the count value, and then you need to enable the exception. So as you know, in the counter count status register in the system tick, bit 1 is for exception, bit 2 is for clock source, and bit 0 you got to enable for the counter. And then we created 4 task handlers: void task 1, task 2, task 3, and task 4. And the main program would look something like this, but we haven't actually gone to do this scheduling algorithm. After you've done this scheduling algorithm, you will have this init scheduler stack, and you will have the init task stack. You will have the switch stack pointer to PSP, and you will call the task1 handler function. And to do that, here you got to use a bit of assembly instructions as well. So if you go to ARM Cortex M4 reference manual on page 34, you got to use these registers, special register. To read the register value, you got to use MRS, read and the special register, and to write, you got to use MSR to write the special register. To save the data, you got to use push instructions with open braces, and you need to tell which register locations you need to be saved, and then you need to link that to the addresses with the link register, and then pop is for retrieving from which you want to do. And bx is used for branch indirect register, and if you write bxlr, that means return from that function call. And then if you want to store multiple registers, in case like we do with multiple registers, you got to use stmdb stmei and the registers and the register list. If you want to load multiple registers, then you need to go for ldmia and register list. You will be learning all this in the program. To do that, you need to use a prototype called attribute underscore naked. So the purpose of the attribute naked is we need to avoid this prologue or epilogue code generation. So when you start to write the attribute, technically it goes in and inside the register it changes all the values, and that will disturb the stack frame. So in order to stop this, you need to write the attribute underscore naked, and this will stop creating this prologue and epilogue registers to be saved inside. So this can be useful for writing assembly code for optimizing purpose for specific platforms. Before going to learn about scheduling algorithm, I'll go through with the theory so you know what we got to do. First off, we got to start with the task control block. So you need to write a task control block. By creating a task control block, you need to set it with a type. The type is the type def struct for a task controller. Then you need to declare your data type for the PSP, the program status value. And then you need to again set the data type for the current state, that's 8-bit. The PSP is 32-bit. And then you need to declare the task handler, which task handler you want to ask that control block to go to. And then you end up with task control block underscore t. And then you need to classify and set how many tasks you are creating by the user. So you need to use this tcb underscore t user task of maximum tasks. And the next step, once you created the control task control block, then you need to get the current PSP value. So to get that, this is the instruction you got to use, and this is what you need to return with the user tasks of current task with PSP value. And then after you get the value, you need to save the PSP value. So you need to use this function to save from the current value and move it to the current task. And then once the current task is done, then you need to update the task to do the blocked state and the normal state, and you got to use this function to tell the stack that the current stack is done, so you need to update that. In order to capture that, to avoid those two attributes, so you need to start with creating two variables, MSR and MSP. So you need to initialize the scheduler stack. So this is where you are writing the scheduler stack. And then you need to create an idle task, because sometimes when it goes to the idle state, it has to go through a task, and you got to write an idle task for that. And then when you start off with every stack contents, you got to load with dummy contents first, dummy data. And this is the function I will show you how to write. And you got to write first current state, and then you need to fetch the value for PSP current value, and then you need to assign that to each and every task handlers. And then you need to store the dummy stack contents for each and every stack. So you got to use this function, and you need to use the all the dummy stack contents to it. And after that, now you store the stack pointer. Now you need to move to the program status value, the register. So to do that, the first step is to preserve the LR, the link register, which connects back to the main program using push. Then get the PSP value of the current task. Then initialize the PSP value. Then retrieve linked register value using pop, and then change stack pointer to PSP using control registers. Then once it's finished, then ask it to go back to main function. So you got to write, in order to accompany all these 6 steps, you need to write an assembly language code like that inside your C program. So this is how you're going to write. And then the next concept is context switching. So this is where you're going to tell in scheduling, if you want to run, if it overruns that 1 millisecond, you need to go to jump to the next task. So that is what literally called as context switching, and these are all the steps you got to follow. First, get current running tasks in PSP value, then use that PSP value to store stack frame 2, because by default we know when the context task have to be saved in the stack frame 1, it saves R0, R1, R2, R12, program counter XPSR, and the link register. The others you need to set as manual. So save the link register using pause operations, and then save the current value of PSP, then decide next task to run, then get its past PSP value, and using this PSP value retrieve all the register context from SF2, that is RF to R11, then update the PSP, then retrieve the link register to use pop operations. This is the context here. Now you are getting it out to so that you can work on the same context, and then you update this PSP and exit. So that is context switching. You will be writing a code like this to run an assistic handler, and this is an assembly language code inside the embedded C. So now let's get in, and I'll show you to include the scheduling algorithm by step. Before that, please go and have that enjoyable break, have your energies up, get whatever you want to do, stretch those arms and everything. So come back and I'll teach you how to write the scheduling algorithm from step 1. Go and enjoy that break. I'll see you in a couple of minutes. So see you then.